Let us discuss today a MO diagram for carbon monoxide. General pattern for understanding of MO diagram will follow. But in this part, I want to follow new trick of teaching. I'll give only lecturing at the beginning. Video lecture will be there. And emphasis will be given for your visualization. Afterwards, each and everything will be made crystal clear through pictorial presentations. So stay tuned. Let me know your feedback about this new strategy, new technique, new method. Yes, students, let us understand now the MO diagram for carbon monoxide molecule. Simple approach let us discuss first. Mixed sp orbital diagram, general sp orbital diagram with which let us try to explain carbon monoxide molecule. In this, which two atoms are there? Carbon and oxygen. What is electronic configuration of carbon? With atomic number 6, 1s2, 2s2, 2p2. What about oxygen? 1s2, 2s2, 2p4. So number of electrons are different, but orbitals are same in both atoms. But energetics is different. 1s orbital is considerably inside. So those orbitals will remain non-bonding. But what do you think? Energy of 1s orbital of carbon and 1s orbital of oxygen, will both energy same? No. Whose energy will be lower? Oxygen or carbon? Oxygen. Energy for the oxygen 1s orbital will be the lower compared to carbon. So what I can consider? S orbital, which symmetry? Sigma kind of symmetry or pi kind of symmetry? Bonding axis is a principal axis, or that's the only axis. Around that axis, if I rotate that orbital, phases should not change. So S orbital is spherically symmetrical. There is no change in phase. So both are sigma. So 1s orbital for oxygen, I'll say 1 sigma, lowest energy orbital. 1s orbital of carbon, I'll say 2 sigma. So now two orbitals are over. Both are non-bonding orbitals. Now come to 2s orbital. From your point of view, let us divide this in three compartments. Left compartment, atomic orbitals of carbon. Middle compartment, molecular orbitals of molecule carbon monoxide. Right compartment, atomic orbitals of oxygen. 2s orbital of carbon and 2s orbital of oxygen. Whose energy should be lower? Oxygen 2s orbital energy should be lower. But they have the same symmetry. Appreciable overlap may possible because outer orbitals are there. So because of their interaction, two molecular orbitals will be there. One sigma 2s and other sigma star 2s. Likewise we are saying. Now how labeling will be there? It is our third sigma orbital. And upper one, 4 sigma star orbital. Is it clear? Now come to p orbitals. 2p orbitals of the carbon and 2p orbitals of oxygen. Among those p orbitals, if I consider x as a bonding axis, x as a bond direction, then 2px orbital will form sigma bond and py and pz will form pi bonds. As per our mixed MO diagram, what will be there? Bonding pi orbitals will be of lower energy. So energy sequence will be, but this is the first category of pi orbitals. So we will label that set of those two orbitals, pi to py and pi to pz, as 1 pi. Afterwards, sigma to px, it is a sigma category. What will be the number? 1s for oxygen, 1, 1s for carbon, 2, sigma 2s, 3, sigma star 2s, 4. So this is what? 5 sigma orbital. Afterwards, anti-bonding pi to py and pi to pz. Label will be second pi orbital. So 2 pi star set. Last orbital, pi star to px. The name will be 6 sigma star. Is new nomenclature clear? So let us fill the electron. In 2s orbital, 2 electron in both carbon and oxygen. In 2p orbital for carbon 2 electrons and oxygen 4 electrons. So total number of electrons now in outer orbitals. How many are there? 10. So how can I put those 10 electrons? 2 electron in sigma 2s orbital, means that's our 3 sigma orbital, 2 electron in 4 sigma star orbital, 4 electrons in 1 pi orbitals, and 2 electrons in 5 sigma orbital, and no electrons in 2 pi star and 6 sigma star orbitals. Is electronic configuration clear? Let us find bond order. Bond order is equal to number of electrons in bonding orbitals minus number of electrons in anti-bonding orbitals divided by 2. How many electrons are there in bonding orbitals? 2 electron in sigma 2s means our 3 sigma orbital, 4 electrons in 1 pi orbital, 2 electrons in 5 sigma orbital. So total 8 electrons are there in bonding orbitals. And in anti-bonding orbitals, how many electrons are there? There is only one orbital where electrons are there. That is a 4 sigma star. Number of electrons in bonding orbitals minus number of electrons in anti-bonding orbitals 2 divided by 2. What is the answer? 3. So what is the bond order? 3. So between carbon and oxygen, 3 bonds are there. 1 sigma bond, mainly due to electrons in 2px orbital, and 2 pi bonds because of electrons in 1 pi orbitals. Now question will be with, what about 3 sigma and 4 sigma? Star. Yes, bonding and anti-bonding, same number of electrons are there. So bond order contribution will not be there. So bond order is 3 and it is a reality. What about magnetic property? It is diamagnetic in nature. So it is a general way of explanation of MO diagram. This diagram seems to be the correct, but supposed to severe limitations. Carbon monoxide is a good ligand. It donates lone pair, means 2 electrons, and by the same time it is a good pi acceptor. Nowhere that explanation is possible by means of this diagram, because whatever outer electrons are there, they are involved in the bonding. Sigma to px, electrons in pi sigma, electrons in 1 pi are involved in the bonding. If they are involved in the bonding, then how it can they be donated other than bonding electrons? Lone pair should be there, then only it can be donated. And carbon is donating. In general sense, more electronegative species donates. Here more electronegative species is oxygen. So donation through oxygen should be there, but it is through carbon. If I remove 1 electron from carbon monoxide, then bond length decreases. But here suppose if I remove the 1 electron from carbon monoxide, means electron from sigma to px, then bond order will be 2.5. Bond order is less, bond length will increase. But what is happening here? Bond length decreases after ionization. So this phenomenon also could not be explained. For that, we need to discuss some modified approach. We'll discuss them later. Let me complete other heteronuclear diatomic molecules. Then I'll come again to the modern approach, modified approach, and explanation of the diagrams. Additional 2 approaches I'll discuss with you. First modification with hybridization was suggested by Coulson. Now let us broaden our vision by understanding this MO diagram somewhat in detail. First, let you know symmetry of this molecule. Point group is C infinity V. What does it mean? There is a C infinity axis that we are considering as a x-axis. In true sense, whatever the principal axis is there, that we should consider as a z-axis. But here various molecules are there and their confusion should not be there. Therefore, I am considering horizontal. Horizontal word is not correct. But whatever C infinity axis, that I am considering as x-axis. Because for other molecules, I am considering z-axis, which will be the up and down. Because how we represent the molecule? Carbon left side, oxygen right side. Atomic orbital of carbon left side, atomic orbitals of oxygen right side. Therefore, I am considering X as a bonding axis. In addition to that principal axis, there are vertical planes. It is a good thing that horizontal plane is not there. Center of inversion is not there. So we are with the wide scope of combination. But in this part, we are discussing simple combination. Simple MO diagram. which will describe few properties of carbon monoxide. Now, electronic configurations for carbon and oxygen are represented there. My point of interest is energetics. Oneness orbitals of both are considerably low in energy. They are inner orbitals, so overlap is not there. So to develop the molecular orbitals for interaction point of view, they are less important at this moment. But for electronic configuration, we need to consider those are part and parcel of the molecule. So those we will consider as sigma orbitals. 1 sigma from oneness orbital of oxygen and 2 sigma is a oneness orbital of carbon. Now point of interest, 4 orbitals S and P from each category. So lowest S orbital, that's a 2s orbital, is of oxygen and its energy is minus 32.3 electron volt. Now I want to combine it with p orbital of the other, that is a p orbital of carbon. And p orbital of carbon is of the energy minus 10.6 electron volt. Actually, SS combination 2s orbital of one and 2s orbital of other, they do combine. But this sp kind of combination, by energetic point of view, not suitable because large kind of energy gap is there. Almost 22 electron volt gap is there. So direct sp combination from oxygen to carbon be not possible. Let us think about other sp combination, means 2s orbital of carbon with energy minus 19.4 electron volt and 2p orbital of oxygen minus 15.8 electron volt. So here hardly difference is of the 4 electron volt. So their combination is possible. So this sp combination directly also may possible. But whatever the impossible combination that I said, 2s orbital of oxygen and 2p orbital of carbon, that may possible via mediators. Means what I wanted to say. 2s orbital of carbon will link to the 2p orbital of the oxygen. 2p orbital of the oxygen will link to the 2p orbital of the carbon. And 2s orbital of carbon is already linked to the 2s orbital of the oxygen. So indirectly, it is not direct interaction. Indirectly, 2s orbital of oxygen is linked to 2p orbital of carbon. Are you following what I am saying? By the way, molecular orbitals once established, those who have the same symmetry, they also can show the energetics. Variation in the energetics that we have studied in the previous part while understanding the nitrogen molecule. Was that molecular orbital diagram made sense of understanding? Yes, students, it's a very important point. So all possibilities that I just wanted to inform to you. Now what I wanted to emphasize, s orbital of one can interact with the p orbital of other, may directly or through via media. Even molecular orbitals are going to interact. In this molecule, since it is a heteronuclear diatomic molecule, horizontal plane and center of inversion is not there. The mixing of the orbitals may possible. So actual diagram may be different one. But in this part, simple diagram, let us know for carbon monoxide. An important thing is written in the small font upside about the ionization energy of carbon monoxide. This will come to use later. See here, simplest MO diagram for carbon monoxide. 1s orbitals are not shown here, but they are there. Lowest orbital is a 2s orbital of oxygen and 2s orbital of carbon is a higher than that. 2p orbitals of oxygen are lower than the 2p orbitals of carbon. Means being oxygen more electronegative, its respective orbitals are of low energy. Energy arrow is represented left side. Resultant orbitals, that's a bonding 2s orbital. I am labeling it as 3 sigma. Why number 3? Because already 1 sigma of oxygen that has taken one number, 2 sigma of oxygen has taken the other number. That 2 sigma, what I am saying, 1 sigma and 2 sigma means 1s orbital of oxygen and 1s orbital of carbon. Then next highest sigma orbital, but it is anti-bonding. Therefore, we are saying it as 4 sigma star. Afterwards, pi orbitals are there. First set of pi orbital. Therefore, I am labeling it as 1 pi. Then sigma kind of orbitals are there. Bonding orbitals are there. So by sequence number is 5. So label is 5 sigma. Afterwards, anti-bonding orbitals are there, but pi orbitals are there. So by sequence of pi, number is 2 pi asterisk. Now last, anti-bonding orbitals are there. Those are preceded by px orbitals. Sigma kind of anti-bonding orbitals are there. Number is 6. So label is 6 sigma star. So is the point of labeling of molecular orbitals clear to you? Then we have to fill the electrons in the respective molecular orbitals. We will get the electronic configuration. On the basis of electronic configuration, we have to find out bond order. Yes, we can talk about the stability. On the basis of electronic configuration, we can comment on magnetic property. On the basis of electronic configuration, we can explain the stability. Are you getting? So let us see the next part. That's calculations on the basis of this MO diagram. Now see the representation of electronic configuration. 1 sigma means 1s orbital of oxygen, 2 electrons. 2 sigma means 1s orbital of carbon, 2 electrons. And 3 sigma is our bonding orbital, 2 electrons. 4 sigma star anti-bonding orbital due to 2s orbitals, 2 electrons. 1 pi set, it is due to the 2py and 2pz orbitals of carbon and oxygen. Total 4 electrons are there. 5 sigma, it is resulted due to the 2px orbital, axial orbital, 2 electrons, and higher orbitals, 2 pi star and 6 sigma star, no electrons. I want to find bond order. What is the formula of bond order? Bond order is equal to number of electrons in bonding orbitals, Nb, minus number of electrons in anti-bonding orbitals, Na. Just count the number of electrons in bonding orbitals. Among these, the orbitals where electrons are filled, no? Anti-bonding orbital, only one orbital is there. That is 4 sigma star and there are 2 electrons. Rest of electrons are there in bonding orbitals. But don't count the electrons present in 1 sigma and 2 sigma. Why? Because they are non-bonding orbitals. They are not fruitful for bonding. They will not contribute for bonding. So what is the ultimate answer? 8 minus 2 divided by 2. Answer is 3. So 3 bonds are present between carbon and oxygen. If 3 are there, then how many sigma bonds? 1 sigma bond. And it is mainly due to, as per this diagram I am seeing, electrons in 5 sigma orbital. And 2 bonds are pi bonds. And those are due to 4 electrons present in 1 pi orbital. See, type of orbital is pi, pi bonding. Type of bonding orbital is sigma, sigma bonding. Now question you will be with, why not 3 sigma? Yes, effect of 3 sigma is cancelled by 4 sigma star. It's a general chemistry point of view, general understanding point of view. At simplest level that I am saying. Therefore, we are not considering contribution of 3 sigma and 4 sigma star as a result. Okay, fine. So 1 sigma and 2 pi bonds are there. So what about stability? It should be more stable because 3 bonds are there and it is true. So bond order quite well explained by this MO diagram. Stability also explained by this MO diagram. What about magnetic property? Is there any unpaired electron in any of the molecular orbital? No, there is no unpaired electron. So all electrons are paired, therefore this molecule will be diamagnetic and it's a reality. Excellent. So this MO diagram, though it's simple, could able to explain bond order and stability. Main problem is this MO diagram cannot explain electron donating, ligand ability of carbon monoxide where carbon is a donor. We are not finding anywhere 2 electrons, lone pair of electrons near to the orbitals of carbon. All electrons are busy in the bond formation. So it's a problem. Other problem is in carbon monoxide, after ionization, removal of 1 electron, bond length decreases. Here suppose if I remove the outermost electron which is present in 5 sigma orbital, those are responsible for bonding, then total bond order will be 2.5. If bond order is less, then stability will be the less. By the way, internuclear distance will increase. So this diagram could not explain the observation decrease in the bond length with ionization. So these main two problems could not be explained by this MO diagram, this MO treatment. So though it is a simple, suffers through limitation. We need to find solution for that. A scientist Coulson had suggested us hybrid model or MO diagram, modern MO diagram considering hybridization that we will see in the next part. If any limitation is there, we need to see further modified diagram. Is this discussion clear? Yes. The purpose to make this video first only lecturing and then this pictorial presentation is clear cut understanding. I hope the concept is clear. Now it's a time of homework. As a homework, I am asking here two interesting questions. Let me see how far you are curious to learn, curious to study, and how much you remember once you listen. In this video, in this presentation, somewhere I mentioned ionization energy for carbon monoxide. What is that value in terms of electron volt? You have to mention in comment box as answer of first question. And second question is, whatever that value of ionization energy is there, from that you will get idea about the energy of outermost orbital in carbon monoxide. As the answer of second question, you have to write energy of highest field orbital in carbon monoxide is higher than the energy of 2p orbitals of oxygen or lower in energy than the 2p orbitals of oxygen. Is question clear? I am waiting for your answers.